Hello and welcome back to Maths with Mr. Duffield. Having another go at some proof questions that I've had requests for help from my Deps class regarding. Let's take a look. Question 3 of this worksheet. The triangle below has a right angle at C, right here. Explain why triangle ADC is similar to triangle ACB. Okay, so I've got my triangle all labelled up here and I'm attempting to demonstrate triangle ADC is similar to triangle ACB, as in the whole thing. So the triangle on the left is similar to the whole triangle. So I've taken the liberty of doing my own sketch here. Here we go. It's the same shape, just sketched in a slightly larger way to enable me to fill in the information that I need to. And another thing that I'm just adding before I begin, if this is C minus X and this is X, then C minus X plus X means that the whole length I can express as length C. That's important for what I'm going to be going on to later. Now, to demonstrate similarity, we know what the word similar means, don't we? We mean two shapes that are enlargements of one another. In other words, the angles that are existing within the shapes are going to be identical. So if I can demonstrate that the angles in this triangle are the same as the angles in this triangle, I've demonstrated that they're similar. Okay, so let's begin. If I choose to label this, what should I choose? I can choose to label this angle here as theta, let's say. So this is 90, this is theta, this angle up here has got to be 90 minus theta. I'm filling in every single angle for a specific purpose. I'll come to that in a second. If this kind of corner at C is 90 degrees, this one angle is 90 minus theta, this has got to be theta. And then this is theta, sorry, this is 90, excuse me, this is theta, this has got to be 90 minus theta in order to add all of these three angles up to 180 degrees. You can think of this as 180 minus 90 minus theta, and then that simplifies to 90 minus theta if you like. Yeah. So these are the angles that I've labelled this diagram with. Triangle ADC has angles 90 minus theta, 90, and theta. Angle ACB, i.e. the whole thing, has angles 90, theta, and 90 minus theta. So I can say that the angles, whoops, excuse me, let me start that again. The angles in ADC and ACB are equal. They are equal. Therefore, ADC and ACB are similar. That is sufficient. If I've got a clearly labelled up diagram here that clearly identifies which triangle is which, and I've identified that the angles are equal in both the triangles, that's sufficient to demonstrate that they are indeed similar to each other. Next little stage of this question, use these similar triangles to write down a relationship between A, B, C, and X. In other words, any relationship between the side lengths of these triangles. Okay, so let's look at ADC first. Effectively, the ratio between, I don't know, the base of the triangle and the hypotenuse of the triangle is going to be the same as the larger ratio of the same. So if I just turn the page around so you can see what's going on here, this is the larger seen from another angle. The ratio of this length to this length is the same as the ratio of this length to this length. Why? Because they are similar triangles. Okay, so let's algebraically label what's going on here. So this divided by this is the same as this divided by this. Okay, that's what I get from the fact that they are similar. Let's write that down. C minus X over B equals B over the entire length, C minus X plus X, C. Okay, that's part one done. Part two is very similar. Explain why triangle BDC is similar to triangle BCA. In other words, BDC is this one here, and BCA is actually the same triangle as ACB. It's just change the letters of the order of the letters, probably in an attempt to confuse. All right, exactly the same idea. The angles are equal, therefore they are similar. I could spend some time writing that out if you like. I think it might just be a bit of a waste of time at this point. It's exactly the same demonstration, just with this written as BDC and this written as BCA. That's it. Okay, use these similar triangles to write down another relationship between the side lengths. Okay, we've done well so far, and we're going to do a similar sort of approach to what we've just done. Okay. Just bear with me as I take a look at my notes here. Yeah, so again, the ratio of this base to this hypotenuse is the same as the ratio, just bear with me, of this base and this hypotenuse, okay? Because they are mathematically similar shapes, okay? So, what does that mean? Just bear with me as I struggle with my webcam angle. What that means is that for the second one, x over a equals a over c. Okay? That divided by that is the same as this divided by this. That's what mathematical similarity means. The ratio of the side lengths are going to be equal. So that is my statement for the second one. Eliminate x from the two equations you have found. What well-known result have you proved? I'm pretty sure you can start figuring out what's going on here. Okay, if I take my second equation here, in fact, let me make some more space up here. So part 3. If x over a equals a over c, that means x equals a squared over c. Okay? I'm pretty sure. Yeah. Just wanted to make sure I got this absolutely right. C minus a squared over c equals b squared. Okay. I'm going to take, so that's the equation in terms of x. The first equation I had was c minus x over b equals b over c. If I times both sides by c and times both sides by b, I get this. C, open bracket, c minus x equals b squared, which is just, that's absolutely fine. These are the two statements I'm going to use. Effectively, I'm going to replace the x in this statement with its value from this statement. Okay? So it becomes c, open bracket, c minus a squared over c equals b squared. Oh, let's multiply this out and see what happens. C times c is c squared. C times negative a over c minus a squared, and then equals b squared. Hang on, let's add a squared to both sides. C squared equals a squared plus b squared. We, my friends, have just formally proved Pythagoras Theorem. That's it. You've seen Pythagoras Theorem explained to you. You've worked through countless examples, but you've never had it formally proved in this way before. From considering two right-angled triangles which combine to make a third and larger right-angled triangles and the similarities between them, you compare the ratio of the lengths, form two equations, rearrange them, sub one into the other, and you've got Pythagoras Theorem. That's really neat and elegant, actually. Very, very cool, and serves as the complete answer to the third question of your exam set. I hope that makes sense. I'll stop recording now because it sounds like someone's knocking through a wall next door. I wish you all the best in all the work that you're doing. I acknowledge that proof is inherently tricky. That's why I've had to continually refer back to my notes throughout this video. Keep practicing, keep going, don't give up, don't quit. I guarantee not all A-level topics are as weird and confusing as this one. I wish you all the best, and yeah, get your work done on Teams. I will talk to you very soon.